Hello everyone and welcome to MLDown. So we're going to start talking about the backpropagation algorithm so that we can understand how we can train deep neural networks where we have many layers of many neurons between our input data and the output of our neural network. Now, in order for us to understand the backpropagation algorithm, we need to sort of lay a foundation about a more basic topic that is called the multilayer perceptrons. Now, we've already seen what a perceptron is. You've got your input layer, you've got some weights that we use to linearly combine our input features together, like that. And then we have this sort of step function over here that determines whether the output of the network is going to be 1 or -1, depending on whether this linear combination, or we've named this the pre-activation, if that is positive, the output of the network is going to be 1, otherwise -1, right? Now, the problem with a shallow neural network is that it is not capable of learning sophisticated functions that would map your input data to the correct output, right? Because it's just simply too simple, right? Because of that, people started talking about the idea of multi-layer perceptrons, where you've got your input data, you've got your output, your output layer, so input layer, output layer, and in between them, instead of having only one layer, you have multiple layers that we call the hidden layers. And if you notice, between all of these subsequent layers, you've got many connections, and you've got many weights, so each connection has a weight, right? So again, this is not a video on multilayer perceptrons per se, so this is just a gentle sort of introduction to what multilayer perceptrons are, just to lay the foundation for the backpropagation algorithms, which is going to be highly mathematically motivated, to be honest with you. So because of that, we're just going to introduce, sort of touch on the idea of multilayer perceptrons. So when you have many layers or hidden layers between your input layer and the output layer, you are suddenly capable of learning sophisticated functions. For example, a self-driving car, and let's say you have this camera sort of mounted on top of a car, and it's sort of it's capturing frames, frame after frame from the streets in front of the car, and the job is for a neural network is to look at those images and decide whether you have to turn left, turn right, hit the brakes, or step on it and just speed up, right? So the output is going to be 4 actions, right? And the input is the frames of the images. Now, because those images, the sort of snapshots of a street, could be really complicated. You could have lights, you could have pedestrians, you could have, different cars approaching with different angles, with different speeds. So because it's very complicated, that is what motivated the idea of deep models or multi-layer perceptrons, so that you could learn those sophisticated sort of functions that could map your input layer to the correct output, or the desired output. Now, we've seen already that in a simple perceptron, this thresholding function or thresholding unit that we've used, it's sort of like, and if you notice here, you've got +1 and you've got -1, and in between we haven't defined what happens there, right? So the output is going to be either +1 or -1, and if the input is 0, it's sort of undefined as to what's going to happen here. I mean, you can define it, and practically speaking, they do define it. To either, I mean, they say that if this linear combination is equal to 0, either output 1 or -1. They do that actually, but there's a problem with this particular function, right? Excuse me, with this particular step function, or let's call this the more general word that is called the activation function. There's a problem with this, and it's that this function is not differentiable, right? At point 0, we have discontinuity, right? So that's going to be a problem. In fact, what we're interested to know is that, okay, we've seen a deep neural network, a multilayer perceptron, aka. We know that we have so many weights between all of these consecutive layers, but we still don't know what is happening inside each and every one of these neurons. What is the thresholding sort of function that we're going to use there? In a perceptron, it's a step function, and the threshold is exactly equal to 0. So what about here? What should you do? Now, you might be tempted to use a simple linear sort of function, meaning that if you think about a given neuron, right, and if you say that, okay, that neuron has a linear function, meaning that you've got your neuron here, and the input data comes in, and then you've got your output, but the function that is happening inside is a line or a linear function, meaning that the input data that comes in and the output, let's call it x hat, that comes out, is going to be computed using this function called f, right? So that is this function, that activation function that is inside that neuron. Now, if f is linear, it means that f of x is going to be exactly equal to x, right? So the output x hat is going to be exactly equal to the input. So you're not doing anything, basically, right? Now, the problem with having so many lines here, like each one of these guys being a line, is that a collection of many lines is still a line. So you are not achieving any nonlinearity. So what we desire is to be able to, because, as I said, we want to learn sophisticated functions, is to, so we have to be looking for some sort of a activation function that has some degree of nonlinearity in it, so that you have a collection of nonlinear functions, activation functions together, mapped into one another, so that a collection of all of these guys together will be a sophisticated nonlinear function. It just has more flexibility compared to a line. Right? So the number one, in order to choose a thresholded or a threshold unit, the number one condition that we are interested in is going to be nonlinearity. That's the first property that we're interested in. Now, what about differentiability, right? So in the previous videos, we've talked about gradient descent and stochastic gradient descent. We've talked about the delta rule, and one thing that you've noticed there is that we need to take the partial derivative of our error with respect to all of the parameters in our network, right? Now, so it means that the error has to be differentiable with respect to those parameters, right? Now, in order for gradient descent to work in a neural network, you need to, so all the functions that you're going to have in your neural network has to be differentiable. I mean, they have to be differentiable. So, for example, if you have, and I mean, imagine this huge neural network, right? But I'm just going to zoom in only one of these neurons, right? Now, for example, if you think about one neuron, right, that has an input and has an output, right? Let's call the input x, let's call the output y, and let's call the activation function f. Remember, I'm talking about differentiability of f, right? Now, in other words, y, which is your output, is equal to f of x, right? In order for gradient descent to work, in order for you to be able to develop learning rules for all of the parameters in your network, which could be millions of them, in order for that to happen, this f has to be differentiable with respect to its input, meaning that the partial derivative of your f with respect to its input, which is x, this has to exist, right? In other words, f has to be differentiable, which means that it has to be continuous as well, right? So you immediately notice that that is not something that we have with the step function. So at point 0 we have, let me choose a better color, at point 0 we have discontinuity, right? at point 0, this step function is not differentiable with respect to its input, which is the input over here, right? Which is this whole linear combination, right? So because we use gradient descent and we have to compute these gradients of the error with respect to each and every parameter of your neural network, we need to make sure everything in between is differentiable, all the functions that we're going to use. So we've already seen that the step function is not differentiable across all of its inputs. In particular, at point 0, it is not differentiable. It's discontinuous at point 0, right? So in order for us to be able to train a neural network, in order for us to be able to train a neural network, we are interested, we want these threshold units, whatever function it is that we're going to use across all of the, across the entire neural network, we want those functions to be differentiable, right? Which a step function isn't, right? This right here is an example of one of the functions that people use nowadays, or one of the units that people use nowadays, and it's called a sigmoid unit. And as opposed to a perceptron unit, instead of having, everything is the same, except instead of having a step function over here, we have some sort of a nice curvy nonlinear activation function that is nonlinear, number one, and second of all, it is sort of a continuous function, thus it is differentiable across all of its inputs, right? And don't worry about this mathematical thing over here for now, but I just want you to know that this is one of the examples of a type of function that you can use in a unit of neural network, or in a huge neural network. You could use functions like this in each one of those neurons in your multilayer perceptron, and you can be sure that, okay, all of these functions are differentiable and all of them are nonlinear, right? So they all satisfy both conditions. So the entire multilayer perceptron is going to be a collection of such strong activation functions, right? And then eventually this will result in learning, being able to learn sophisticated functions between the input and the output, right? So that is great. Now, is this the only type of function that we can use that will satisfy those two conditions? No, that's not. Actually, sigmoid is becoming less and less popular. Nowadays, people use functions like tanh, or that's also called hyperbolic tangent. They also use ReLU, which is a very, very interesting activation function, which, funny enough, is not differentiable across the board, right? Again, there is some non-differentiability there when its input is 0. But I have a video on that actually, and I've explained exactly how the non-differentiability could sort of, get circumvented, and we could still learn very interesting functions using our deep models. But I don't want to digress. Actually, sigmoid has a couple of problems, but this is not the topic of today's talk. So I'm just gonna leave it at that. That basically speaking, we are interested in functions that are nonlinear and they're differentiable, right? So this is a sigmoid function, right? Mathematically speaking, the sigmoid function, the notation for it is some sort of a notation like this. So sigmoid of x, whatever its input is equal to 1 over 1 plus e to the power minus x. So this is the math of it, right? So the horizontal axis over here is your x, right? And the vertical axis is your sigmoid, right? Now, if you notice, we have a good deal of nonlinearity over here, this part over here, and a good deal of nonlinearity over here. So we have some nonlinearity going on. Unfortunately, we have sort of flat lines on the extremes, right? And we have some sort of a linear behavior in the middle, right? But the good news is it is differentiable with respect to x, right? So the partial derivative of our sigmoid with respect to its input exists for all x's, right? Now, one thing you need to notice here, I mean, not need to notice, but it's interesting to know, is that when input data, when, you know, x is exactly equal to 0, which is this point, where x is equal to 0, sigmoid of x at x equals 0, which is this point, lies at 0.5, right? Which is interesting because, you know, the maximum value that you could get out of a sigmoid, which is at this extreme over here, the maximum value that it sort of converges to is +1, right? Which is this value over here, +1. It's a little bit small, can't be read properly, but that is what it is. And over here, the minimum value that you can get is 0, right? So no matter what x is, sigmoid always squashes that x between to a value between 0 and 1, always. That is why they also call it the squash function, because it literally squashes x or its input, basically. So so the minimum value is 0 and the maximum value is +1, and the midpoint is exactly 0.5. And when does that midpoint happen? It's exactly when the input is 0, right? So at x equals 0, we are in the middle. Now, I just want to sort of introduce you to what sigmoid is, but what the message I want you to get out of this slide is that a sigmoid function is differentiable across the board, across all of its domain, and it is also a nonlinear function, right? So it seems like a reasonable choice for our neural network. Now, what happens if I actually mathematically compute this partial derivative, right, and plot the result? Funny enough, the plot looks something like this. Very interesting. It looks like some sort of a Gaussian function, and this is the partial derivative of sigmoid with respect to its input. Now you notice that at x equals 0 to 0, we have the highest amount of gradient, which happens to be exactly 0.25, right? And as you increase your x or decrease your x, your gradient sort of goes down, and eventually your gradient reaches 0 on these two extremes. But the gradient is maximum when the input is 0, right? And that is 0.25. Now, you might be a little bit confused as to, okay, what does this really mean? So he was talking about sigmoid, and now he's talking about the gradient. What does it really mean? I've always found plotting the function and its derivative together on one plot gives you a good idea as to what the relationship between the two actually is. So both of them together look something like this. So the blue line is your sigmoid, and the red curve is your gradient, right? Shows the gradient of that sigmoid. Now, if you notice, so gradient is the slope of the tangent line, right? Or the rate of change, basically. So the higher the slope, the higher the rate of change, right? Now, without me telling you, I mean, just ignore that red curve. You already know that. So the slope of the tangent line. Let me choose a better color. Maybe black would not be terrible here. Maybe. So the slope of the tangent line over here is 0, right? It's flat. And the slope of the tangent line over here to your sigmoid is 0. Now the slope over here at this point is teeny tiny bit, but still something. Now over here, the slope is a little bit higher, meaning that the gradient is higher, but at point x equals 0, exactly here, right? This is your slope. That is the highest slope you could get out of your sigmoid function. This means that the highest slope of a sigmoid function happens at x equals 0, right? And that highest slope is exactly 0.25. And that is why that the red curve of the gradient hits its max exactly at x equals 0. And you notice that as you go to the extreme over here, the gradient is 0, and that is already confirmed by the slope of all of these tangent lines, that the slopes, as you go to the extreme, they become less and less and less and decrease and all the way, and they approach 0, right? Same story to the left hand side, right? So over here we have the maximum slope, and as you go down, the slope becomes less and less and less and hits 0, right? So if you keep a record of the actual value of these slopes and plot it, the red curve is what you get, right? So as you notice, the red curve exists everywhere, so meaning that we have a gradient across our blue sigmoid curve across the board. There is a tangent line and there is a slope for that, right? And you very well notice that your sigmoid is actually a nonlinear function, so which is one of the conditions that we want for our you know, the activation functions that we want to use in our, you know, multilayer perceptron, right? So if you use a sigmoid, or let's just say, let's not limit ourselves to sigmoid, shall we? So let's just say if we use a differentiable and non-linear activation function across the board, right? So you'll have some sort of a, you know, activation function for each one of these neurons across the board. And you know that it's differentiable, meaning that if you take the derivative of whatever you get in the output with respect to its input, it exists. Doesn't matter what the input was originally, because that function, whatever it is differentiable with respect to its input no matter what the value of the input is, right? So that is great. And the functions are already nonlinear, right? So a collection of all of these nonlinear functions is going to be a very sophisticated nonlinear function that is, guess what, again, differentiable, right? And you'll see why we really focus on this differentiability, because the backpropagation algorithm is built on the foundation that gradients of all of the functions across the neural network exist, right? So it doesn't want to, you know, the backpropagation algorithm doesn't want to think that, okay, maybe sometimes the gradient doesn't exist, so how am I gonna, you know, learn the parameters of my model, right? But anyway, this is just the foundation for the backpropagation algorithm. That's going to be the topic of the next video in this playlist. I think this is enough for today. So in this video, in summary, we talked about what are the conditions that we expect from an activation function, and we said that differentiability and also nonlinearity are desirable for sure. And we also said that why we need a deep neural network, namely a multilayer perceptron, it was simply because we can simply learn more sophisticated functions between our input layer and the ultimate output, or the predictions that the model is going to make for us, right? So in the next video, we're going to start talking about the backpropagation algorithm, and then everything is going to sing together, because you'll see the connections as to why we keep insisting, especially on this differentiability, right? So I hope that this has been informative for you. If you have any questions, just feel free to you know, post them in the comment section down below. And if you enjoyed this video, feel free to subscribe to the channel, and also click on the bell-shaped reminder so that you'll be notified whenever I upload a new video. And make sure to check out the website www.mldon.com. We have very nice posts, blog posts over there. By the way, I'm going to put a link to the blog post related to this very video in the description below. And you can follow us on Twitter, LinkedIn, and also Facebook. So I think that's it for today. On behalf of MLDown, take care.